morning, friends. What we have decided by reviewing all those forum questions, that we need to have one or two such sessions where I can revisit whatever we have discussed in this course and try to touch the salient points. This you can treat as a tutorial, this you can treat as a Man Ki Baat, but this week completely I will try to revisit whatever we have discussed and underline the salient points. If you see, we started with, let me give a name for this, revision 1. And if you see that when we started this course, we used one term called static stability. We use terms like equilibrium, also we use a specific term trim, and then we also talked about neutral point, we also talked about elevator required for trim. Then as we progress, we glance through lateral directional case and then finally came down to dynamic stability. Okay? So let us first start with static stability. What was our understanding, or what is our understanding as far as static stability is concerned? We said if a body in equilibrium is disturbed and if we observe that it has initial tendency to come back to equilibrium, we said this body is having static stability. Okay? And we try to explain through this sort of a diagram where this is the equilibrium, and by equilibrium we all understand that at this condition net force and net moment is 0. Okay? And how we explained, we said if it is disturbed from this equilibrium and once the disturbance is withdrawn, if it has initial tendency to come back to this equilibrium, we say it is statically stable. And you can see that for such a diagram, there is a force here, component of gravity, and this ball will roll here like this, right? But when you talk about static stability, it was the initial tendency. That's more important. We are not talking about the dynamics at all. We are not talking about the transient at all. Only the initial tendency. If it is having initial tendency, we said it is statically stable. So what was the key word for static stability? It is the initial tendency to come back to equilibrium. Okay? We try to explain this through mass spring system. This is spring, this is a mass, and if I stretch it somewhere here and release it, it also has initial tendency to come back to this equilibrium. It may oscillate. Like that is not the point of concern as far as static stability is concerned. It is only the initial tendency that matters. Okay? Now from these two examples or these two illustrations, when we are talking in terms of aircraft, what we said? Let's see, this is aircraft, let's say it's only wing aircraft or flying wing type concept, and we said, let's say this is the center of gravity, and we define a term called AC, which is aerodynamic center. And what was aerodynamic center? Aerodynamic center is that fictitious point about which the pitching moment is independent of angle of attack. What is the pitching moment? Pitching moment, it is the moment about aircraft y-axis. What is aircraft y-axis? We have been following this convention. If this is x, this is y, and this is z, the right-hand system. So what is pitching moment? Pitching moment is about y-axis. Okay. So what is aerodynamic center? It is that fictitious point about which this pitching moment is independent of angle of attack. And what is angle of attack? We also understand if this is the airplane, this is the wing, and let's say this is the chord line, and if this is the velocity vector, the angle between this reference line and the velocity vector in the vertical plane is defined as angle of attack. Okay? So we now understood or reconfirmed our understanding that aerodynamic center is that fictitious point about which the pitching moment is independent of angle of attack. Pitching moment is independent of angle of attack. Now, we also understand that if this is a body, for any angle of attack, there will be pressure distribution, and the net force we can represent at center of pressure. And you know what is center of pressure? The center of pressure is that point resultant of these forces, whatever acting here and there. In fact, there will be pressure distribution over top and bottom surface, and once we integrate this pressure over area, top and bottom, we get resultant force, right? And depending upon the pressure distribution, depending on the geometry, we can find out the center of pressure, right? Like we have center of gravity, okay? But what we will be doing here, we will not represent the forces and moments acting at center of pressure. What we will do, we will say the forces and moment will be represented at aerodynamic center. So I'll represent CL, CD, CM. Instead of putting all those things at center of pressure, we will be transferring them and represent as if their resultant is acting at the aerodynamic center, because we have additional advantage that about aerodynamic center, the pitching moment is independent of angle of attack. That helps us. And typically, we also know for a low subsonic wing, this aerodynamic center location is, if I measure from here, and if I write it XAC, then this XAC is typically C by 4 for low subsonic speed. For a conventional airfoil. Okay? But as I increase the speed, as it goes to higher and higher speed, that is from incompressible to subsonic, subsonic to high subsonic to supersonic, this aerodynamic center shifts backward. Shifts backward as Mach number increases. This is the understanding of aerodynamic center. Okay. Once we understand this aerodynamic center, now we will try to see for an aircraft what is our understanding about static stability. So I will draw again here. Let's say it is a flying wing configuration, and if this is the center of gravity of this flying wing, so this is flying wing, and let's say the aerodynamic center is ahead of center of gravity. Okay? One combination is possible. Now see, we are going to ask a question whether this is statically stable or not. So how do I do that? I introduce a disturbance in terms of angle of attack. The moment I do this, I know by now there will be CL, there will be CD. So now this force is ahead of CG, and for small angle I can make it much simpler. I can write this is AC and this is CG. For small angle, let's say this is CL. Then what will happen? As I have introduced angle of attack, because the CL will be there because of this angle of attack, and this will give a moment about CG nose up. You see that force is here, so this will give a nose up moment. So now you could see it doesn't have any restoring tendency, or doesn't have any initial tendency to make alpha 0, because this is alpha. So actually, if it is statically stable, it should do like this, so that the net alpha becomes 0, or net alpha becomes whatever originally it was, right? So if AC is ahead of CG of the airplane, or for this case flying wing, then we say this aircraft is statically unstable. And what we also realized, for the same configuration, if CG is here and AC is here, and you could see that if there is a alpha disturbance, that is, when I say alpha disturbance means what? Suppose the airplane is cruising at alpha 2 degree, and because of some upward gust, the angle of attack has become 2.5 degree. So this 2.5 minus 2 degree, this 0.5 degree is the disturbance. So now if that disturbance is there, since AC is behind CG, and I can draw this CL, and this will give a nose down moment, nose down pitching moment. So it will try to come back to that whatever original alpha was there. It will discourage any increase in angle of attack, or it will have an initial tendency to come back to the equilibrium. So this configuration where AC is behind CG, we say the aircraft is statically stable. This is fine for a flying wing. But when you talk about an aircraft, what happens? When it is an aircraft, if I draw an aircraft, suppose this is an aircraft where it has a wing. Now, let's say the AC of the wing is ahead of CG of the aircraft. If this is the combination, then if I ask you a question, as far as wing is concerned, will it give static stability to the airplane? The answer is obvious. Since AC of the wing is ahead of CG of the aircraft, this will give unstable contribution towards static stability. Right? You can understand very well. If there is a alpha disturbance, there will be a CL here. This CL will give nose up moment. It will further increase the angle of attack. So the wing will provide unstable contribution as far as static stability is concerned. But now if you want to make it statically stable, what can I do? The question is this. And that is where the concept comes. We put horizontal tail. Now what is happening actually, you see? If there is alpha contribution or disturbance, say delta alpha acting at the wing, And let's assume that same delta alpha or delta say delta alpha 2, I call it delta alpha 1, only I am being a little bit of cautious that I know that angle of attack at tail and wings will be different, which you know because of downwash. Barring that, please understand, if there is a disturbance of delta alpha at the wing, it will give a nose-up moment. So it has a tendency to increase the angle of attack. But what is happening at the tail? The tail aerodynamic center of the tail, which is behind center of gravity of the aircraft, so it will give stabilizing contribution. But physically what will happen? Because of this, there will be a CL tail, and this moment arm is large enough that will give a nose down moment. That is, it will try to decrease or try to come back to the original angle of attack. So depending upon which contribution is more, this destabilizing contribution because of wing and stabilizing contribution because of tail. And if stabilizing contribution of tail is more than destabilizing contribution because of wing, then this airplane will provide static stability. Correct? That is the basic understanding. Okay. Now, from here we started talking in terms of Cm versus Cl graph. So remember, Cm, the pitching moment coefficient, we defined as pitching moment divided by half rho v square S C bar, and C bar was mean aerodynamic chord. What we have noticed for static stability, even for a flying wing, that if this is the aerodynamic center, if this is the center of gravity, so if there is a disturbance in terms of angle of attack, this combination will give a nose down moment. So pitching moment will be nose down. Nose down is, as per our convention, it is negative. So what we realize for static stability, if there is a positive angle, then the pitching moment coefficient Cm should be negative. Right? For negative alpha, it should be positive. So with this understanding, we developed Cm versus alpha graph, and we said these are the possibilities. If you see between 1 and 2, first we identify what are the equilibrium points. So equilibrium points are point where Cm is 0. So A and B are equilibrium point, and we know that if you want to ensure that it is statically stable, then this dCm by d alpha should be less than 0, because for a positive alpha, Cm should be negative. For a negative alpha, Cm should be positive. With this understanding, we translated this understanding in a mathematical form. We say the slope at equilibrium should be negative. And we identify the equilibrium points are A and B, and you could see the slope at A and slope at B are negative, so both are statically stable case, right? But what was the difference? We found out, said after all at trim or equilibrium, I want positive alpha so that the lift is positive. After all, lift equal to weight is one of our equilibrium point. Of course, we also debated if it is a cambered aerofoil wing, then you can have lift, positive lift even at negative angle of attack. But we are not considering that. Okay. So these are the trim points we realized, and you said the slope about this trim point should be negative. Now between these two variation 1 and 2, we realize that this corresponds to alpha equal to 0 and this corresponds to alpha positive. And our requirement is I want to design an aircraft whose Cm versus alpha should be closer. Typically, it should be like this, not this, because when it is following the trend of figure number 2, then we can generate positive alpha, and I need positive alpha for generating lift, positive lift. And that is how we now further put another condition that for static stability it is fine, dCm by d alpha less than 0, but for trim at positive angle of attack, we said Cm at alpha equal to 0, or which is denoted as Cm naught, should be greater than 0. So this is the condition we put mathematically through our understanding of aircraft in terms of static stability and trim, right? So what is the nutshell of our understanding as far as designer is concerned? That we need to ensure that dCm by dCl less than 0, or dCm by d alpha less than 0, and we know this is equivalent to saying dCm by dCl is less than 0, because Cl is Cl naught plus Cl alpha into alpha. Second thing, for trim, we want to ensure that Cm naught is greater than 0. So finally, we are focused to a variation of Cm versus alpha like this, where this is Cm naught and this is Cm alpha. The catch point is Cm alpha, that is slope of this line, at trim, that is at this point. That is important. This is your trim point. Right? Clear? We are talking about Cm naught greater than 0, and we also realize that Cm naught will be because of Cm naught wing plus Cm naught tail plus Cm naught fuselage. I will just try to revise the Cm naught wing. Please understand that if you are using a cambered aerofoil wing, then suppose this is the CG, and let's say this is the AC of the wing, and let's say this is XAC and this is XCG. I put a bar, you know by now what is bar. It's non-dimensionalized with mirror aerodynamic chord. But since it's a cambered aerofoil, we know that when I represent at AC for a cambered aerofoil CL, this is CD, and there will be CM AC wing, right? This you know this. So if there is a CM AC wing, and of course CL and CD, then you know that if I want to calculate Cm naught, that will be of the wing, that will be Cm AC wing, right? Then plus CL naught into XCG bar minus XAC wing bar. Please understand here that CMAC wing for a cambered aerofoil is less than 0, but our aim is to ensure that Cm naught wing should be positive or less negative, because finally we want Cm naught wing of the whole airplane to be positive. Okay. This is negative, so I should try to nullify or marginalize this value through this expression, and that is possible only when the XAC of the wing is ahead of CG. Otherwise, this will become negative. So if XAC of the wing, let's say this is XAC of the wing, is the aerodynamic center, and if this is the center of gravity of the airplane, so this is XAC of the wing, and this is XCG aircraft. Now you could see that if AC is ahead of CG, it is giving statically unstable contribution doesn't matter. As far as Cm naught of the wing is concerned, if we put AC ahead of Cg, then only these terms becomes positive. Right? We are not much bothered about wing's contribution towards static instability because we have a tail, we'll adjust stability through the tail. Right? So this is very, very important. You should not forget this relationship. Okay.